So here we go, doing another morning of open source hacking and streaming it over the internet just for fun. Like always, I'm streaming out of my home office, so there's kids running around in the next room. There's a dog at my feet sleeping quietly for the moment. And the topic is hacking on RaptorJIT. So RaptorJIT is a fork of LuaJIT. LuaJIT is a really good just-in-time compiler for Lua, but LuaJIT went into maintenance mode a couple of years ago, and there's a lot of more features I would like LuaJIT to have. So I made a fork called RaptorJIT to kind of go forwards, add a lot of features that I've found the need for in the last kind of 5-6 years of usage on the project. So the topic is really benchmarking. I'm continuing a little bit from what I was hacking on yesterday, but I'll recap also partly because the problem has evolved a little bit. So this is my little to-do list for the morning. See what we get through. First, I'm going to revisit the R graphs that present benchmark results. So I have a couple of images that get kicked out of the benchmark script. We'll look at the low-level detailed one first. This is one that I've had for a while. This is just summarizing the results for a bunch of benchmarks with two different versions of RaptorJIT. So in the top left, this panel is a benchmark called Array3D. We have two versions of RaptorJIT that we tested, the latest one and an older one. Each one was tested 100 times, and each result is plotted as a little circle. In this particular graph, the results have been normalized, so instead of saying how long the benchmark took, we express that as a percentage, how much faster or slower it was than the average performance of the first version tested. So in this case, it's normalized by the average performance of the red dots here. So in this case, we see that most of the results were pretty consistent, but there were some kind of outliers on the tail. We saw a little bit more of that on the red one than on the blue one, but it's not entirely clear whether that's due to any systematic difference or just random jitter. So the point there of running the benchmark a lot of times is that we can actually characterize how steady the result of a benchmark is, and this allows us to write more interesting benchmarks. We can write benchmarks that actually specifically try to provoke bad behaviors out of the JIT compiler, and then once we've quantified those, then we can actually teach the JIT how to defend against them. So it's this kind of adversarial process. But what I'm doing now is setting up continuous integration to run these benchmarks automatically when branches are updated on GitHub. And this is going to be a blessing and a curse. It'll be a blessing because we will always have this report up to date to compare, for instance, a release candidate with a release. I haven't started making releases of RaptorJIT yet, but it's quite close on the horizon now. So, so it's kind of time to get the systems in place. But the curse will be that these have to be interpreted, so there's no use generating the reports unless you're actually looking at them and making some use of them, and that can be a lot of work because this is a big image, right? We have quite a few benchmarks, and it's a little bit subtle when you look at some of these. You know, is sometimes like here is a striking difference. This one was much faster than this one, which is great. Here it's a striking similarity. These two were obviously exactly the same, but yeah, others are a little bit less clear. These ones, it kind of looks like the red one is a little bit higher than the blue one, and so on. And I don't want to every single time I push to GitHub have to go through this process of checking each and every panel. So I want to somehow optimize the process of interpreting benchmark results, especially for simple cases like if I push a bug fix somewhere and I don't expect it to have any performance impact. I'd like to quickly do a sanity check and see if it did, you know, have some impact when it wasn't expected to, and that kind of thing. So for that, I thought a little bit about this yesterday, and what I came up with after I turned off the stream was a visual approach, which is this one. So the way this is a single summary of all those panels that we saw before. So I took all those panels, I took the data from them, I squished them all in together, and I made this graph, which works like this. So I have to zoom in a little bit to make it intelligible. So on the x-axis, what we have is elapsed time. So this is when the benchmarks start running, and then time measured in CPU cycles is going forward. This is when 5 gigacycles have elapsed. This is 10 gigacycles. Sorry, I was wrong there. That's the time that the first benchmark completed. Anyway, so on the x-axis we have time going forwards, and on the y-axis we have the percentage of benchmarks that have completed by that time. So this is, you can think of this as like the progress bar from 0% to 100% on the y-axis, and what we see is what was the reading on that progress bar at every point in time. So what it's telling us is how is the progress bar progressing from 0 to 100, how jumpy it is, and how long it takes to get to 100, and this kind of thing. So that's what this graph is telling us. And that's interesting because if we had two versions of the software that actually had significantly different performance, you would expect to be able to see some effect on the progress bar, so to speak, of how many benchmarks have completed. So, okay, so to be a little more specific about what the progress bar means, suppose that you have, say, 2,000 individual benchmarks here. Suppose you started them all at the same time, and then what we're looking at is how many of them have finished at each given point in time. So if we were, say, after 5 gigacycles, we scan upwards, and it's somewhere around here, about a quarter of the benchmarks have finished after 5 gigacycles for both the red software and the blue software. And I haven't drawn a line, but rather a confidence band here. I used this this test that we talked about yesterday, the Kolmogorov-Smirnov test, to just put a little bit of a confidence band on, because we run the same benchmark a lot of times, and sometimes for some of the benchmarks we get a varying results. We get a distribution of results rather than the same thing every time. And in that case, it's very nice to be able to, in some simple way, statistically account for the kind of random variation there. So this is a confidence band to say that we expect that the reading on the progress bar will be somewhere inside this region. We don't give a single value. We don't say we think it will be exactly like here. We don't say that we think it will be exactly 35%, or rather we say it'll be somewhere between 35 and 40%, something like that. So the way that we interpret this graph then is we make a comparison where we look for anywhere like this, where we are confident that at this point in time, where are we? After about 8 gigacycles, it's telling us that we're confident the blue branch will have completed more benchmarks than the red branch. That's what this gap means. So when I'm scanning to just see if anything interesting happened in a benchmark, this is what I'm going to be looking for. Were there any gaps? If there was a gap, then I think I need to look at the other panel, and then I'm going to find something interesting there. If there wasn't a gap, then I'm probably not going to find anything interesting in the other panel. So that's the way that this graph is going to be used. And so if you send me a bug fix to RaptorJIT, this is how I'm going to sanity check it. I'll run the benchmarks and I'll see were there any gaps, and if so, then I'm going to want to account for that specifically. So what we're going to do is we're going to finish what we started, which is to completely automate the execution and publishing of these graphs for certain selected branches on GitHub. So when you go to GitHub, for like the master branch and the development branch, there will always be up-to-date comparisons with these with these particular graphs for troubleshooting performance. So I did a little bit of hacking on this yesterday, and there were a few issues that I have either solved or at least got a lead on. So there was a build error in the R report when I tried to run it yesterday. I got a kind of recurring error at the R prompt, and I wasn't sure what it was. That turned out to be something simple. I had in the previous stream from before, I had made a fix to the way perf was used. I have a little awk script that interprets the output of perf, and it needed to be updated. And I had made that update on a topic branch, and I hadn't merged that into the code I was testing yesterday. So the CSV file wasn't correctly populated yesterday. I fixed that. And another thing that I did is every time I changed the R report yesterday, it ended up wanting to rerun the benchmarks. And this is a decision that gets made by Nix, which is the kind of the build tool that's responsible for running everything and tracking all the dependencies. And I was confused about why the benchmarks reran when I hadn't changed the definition of the benchmarks. I only changed the definition of the report that comes afterwards. And I found a simple explanation for that. So if we look in the directory, into the right window, we look into the test suite benchmark directory. Here we have all of our benchmarks, the array3d.lua, binary cheese.lua, but we also have the R code for interpreting the results. So I put all of this stuff in the same folder in the repository, and then when I run the benchmarks, I make that folder visible. It's part of the build environment, and this means that the validity of the benchmark results depends on this whole folder being unmodified. So anytime I change anything in that folder, it changes the test environment for the benchmark, and that for Nix that means that a dependency has changed. The SHA-256 of the source input has changed and needs to rerun. So there's a really simple solution to that once I know what it is, and that was to just update. This is the Nix derivation, which is kind of like a make rule that runs a benchmark. And what I did was I got the source here, and I said I want to get source files only by specific suffixes, which is Lua files and text files. So it's going to not take any of the R code or the Nix code as an input to the benchmarks, which means that the benchmarks are only going to rerun when I modify .lua and .text files. And just comparing that to what I had before, I used to just take a cleaned up version of the source tree, but now I just take a few specific files. So that solved that problem. So now what happens is I can run the benchmarks. So the benchmarks can be run interactively. You ask Nix. So nothing has happened there. But if I would change the report in some trivial way, I could rename the file from significance to summary. It's not a bad idea. Then if I rerun this, what was happening yesterday is it went off and it ran all of the benchmarks again, but I'm running about, I don't know, it's several thousand benchmarks here, so it takes a while, 20 minutes or something, not a terribly long time, but it's not a nice edit, compile, run loop. So now that I fix the dependencies, I can run that, and I get a much quicker result. And there I see the build result, and now I have the file called bench summary, which is nice. So that's all kind of nice. Those were some niggles and problems that I had yesterday, and now the image that I showed before up here, that image actually is the output that comes out here. So that's the contents of this. That's the contents of this file. So now what I want to do is it's really nice to be able to run the benchmarks locally like this, by the way. So I will do this, and other people can do this too. So if you're hacking on RaptorJIT and you want to run the benchmarks yourself, it's just a one-liner like this. Nix will then go off and it will download R, it will download all the right versions of all the R dependencies, and it will just take care of the whole dependency picture so that you can reliably run your benchmarks and generate the reports without having to deal with the software ecosystem around there, which is handy. Thank you, Nix. But what I want to do now is get it running on the continuous integration, which is Hydra, which is kind of like Jenkins but based on Nix. And I started on that yesterday, and I got stuck, and now I know why I was stuck, and we're going to fix that. So the way I got stuck is that I have, so Hydra didn't allow me to build my Nix expression. It didn't like the way I had written it, and there's a very specific reason for that, which is I have this code inside my Nix build script which specifies what software should be used for, well, for R and for GCC and for basically everything. And this is pinning everything to a really specific version. So I'm going off to GitHub and I'm getting a specific commit of the Nix packages repository. So that's kind of like, you know, if this was Debian or Ubuntu or something, you would be picking one very, very specific set of all the packages. And the idea is that this is pinned. So if I change this URL, then that redefines the software ecosystem that is used. And if I don't change this URL, then everything stays fixed. So it doesn't matter what you have on your computer when you run this. It doesn't matter what distribution you're running or anything like that. Nix is going to go off and run the RaptorJIT benchmarks using exactly the software packages specified here, which will include everything from R to libc. But Hydra, the CI, it's very strict about making things reproducible. So if it builds something once, it wants to know that the next build is going to be the same. And it doesn't, this, as far as it's concerned, this is going out on the internet and downloading some random file because I just gave it a URL. So normally if you want to download a file off the internet, you have to give the SHA-256 hash that it's going to have. That's the way that you promise the CI that you know what it is you're importing and it's not changing. So that, in principle, that's what I would do here. In principle, what I would do here is I would just say the URL is that, and the SHA-256 is, and then I would run nix prefetch, you know, to get the hash. But that only works in the latest version, the very latest unstable version of Nix, actually, for this specific primitive fetch tarball. So if I would do this, that I'm introducing a dependency on the latest kind of pre-release version of Nix, and I don't want to do that, so I'm going to find a different solution instead. And the solution I'm going to use is to let Hydra go off by itself to GitHub and download this URL and feed it in as an external input into the whole build. So it's going to be responsible for that. So I'm going to update my script so that instead of inside the code here it goes off and fetches that, it's going to at least optionally it's going to let that be passed in from an external source, which will be the CI. And I tried doing that yesterday, but I did it wrong. And the reason I did it wrong is that here I say I fetch the tarball, which basically produces a directory on disk containing all the package definitions, and then I said import that, which loads it into Nix. It like runs the Nix code to turn it from a Nix source code on disk to a live definition of packages. But when the CI passes it in, it's not going to do this import step. It's just going to fetch the file. So I need to refactor this a little bit so that I don't expect the CI to pass in something that's already been loaded and imported. That I'm happy with just the files. So what I'm going to do is I'm going to replace this file packages.nix with another file called nix.packages.nix, which will just have a different interface. It will just fetch the tarball without importing it. So the interface is different. If I'll need to do the import separately when I use this one. So now I'm just going to grep through. Over here, I'm going to grep through. Actually, I'm going to do this in another working directory, which is here. I'm going to replace every use of packages.nix with this new Nix packages. So here is the main entry point for the RaptorJIT build, where I import the packages. So instead, I'm going to say Nix packages is like that. Then I'm going to say let packages be for Nix packages. Okay, so this is just a little refactoring. So now, instead of having an argument called packages that it expects to be passed in, it's going to want a package. It's going to want to have Nix packages passed in. And it's going to import that like this. So I hope that this will not change the functionality, but just make the interface a little bit different. and I'm not a Nix guru, but I'm going to make this work. I'm going to do the same thing in this subdirectory, which is for the test suite. It also has a Nix API for running the test suite, and that's going to say Nix packages is import like this, and it's going to say if import. So with any luck, this will run the same way. Let's check. Run the benchmark again, see if it builds, and see if it manages to cache everything. So with any luck, this will be just a refactoring or kind of a change to the external Nix API. Okay, so it's just another dependency thing. So when I build RaptorJIT, interesting. Okay, I think the change was probably successful, but I did update the source tree sufficiently that that when I rerun the build, it wants to rerun the tests. That's because when I put this this filtering code in, I did it down in the benchmark subdirectory. I didn't do it up in the top level of RaptorJIT. So if I hack the Nix code for RaptorJIT itself, then it will want to rebuild RaptorJIT. And if it's rebuilt RaptorJIt, then it will rerun the benchmarks. Anyway, that's fine for now. I'm gonna just assume for the moment that that this works, and I'm going to push it to a temporary branch where the CI can see it, and we're going to try testing it out. So what I'm going to do now is just do a quick sanity check. What I have in my working tree. So I have I've got an update to the R report with that new graph, and I've got this refactoring, and it would be nice to split those up into individual commits, but I'm going to do that separately. For now, I'm just going to push this to a development branch where I can test it on the CI. So I'll say git commit. Overview. And I will push this to, do I have any remotes to find here? What will we call this branch? Do we have a name for it already now? Give the branch a local name, which will be RaptorJIT CI bench, and we will push that to an upstream. So now we have that code on GitHub, so now we can try importing it into the CI, where the edit compile run loop is actually a little bit longer, so fingers crossed that it doesn't require too many tries to get it running properly. So here's the CI. This is a Hydra instance. Again, that's like Jenkins, but based on Nix. It's my favorite CI, the only one that I like. Go into the job set that we started working on yesterday here. We have a job set, which is a job. This is going to download the master version of RaptorJIT and download the next version, which is the development branch, and it's going to benchmark them on the benchmarking code to compare them to each other. And it's only doing a small number of runs initially, just for test purposes, and then once things are working, we can beef it up a bit. It already takes a packages argument, which I'm now going to call Nix packages, where it's going to feed in the software versions that should be used for the test. So that's what was previously specified in the source file, which the CI didn't like, and now I'm letting the CI define the software environment. Anyway, it's a bit obscure. And so the thing is that I want to run not with the master and the next branch, with this testing code that I have. So I'll actually redefine both of these branches to point to my own RaptorJIT was it CI bench? Let's check what we called our branch. RaptorJIT CI bench. Okay, so I'm going to have symbolic name for the first branch will be master. The symbolic name for the second branch will be next. But in fact, the code, they both can actually be running the same code, and it's going to be this experimental version that I just pushed. And it's only a small number of runs. We're going to get really fat confidence bands expressing a lack of confidence in the results. And that's fine. And if it works, then we'll beef that up a little bit, and it'll be an interesting test actually, because when we compare a version of software to itself, then we should have a very high likelihood of having the confidence bands overlap all the way along the way. So it's actually a kind of a useful sanity check. If there would be gaps in the confidence bands, then we would be very unlucky, or more likely the script would be broken somehow. So let's take a look. Evaluation is pending. Okay, so there's not much we can do here except sit and refresh, and I think it's only going to take a short time. Yeah, so undefined variable packages. So I think I maybe goofed my code here. Let's see. Ah. Okay, so I'm referencing this before I do the import. Okay, so let us see how we fix that. So what I'm going to do is I'm going to define the packages as well. Instead of doing it down here, I'll do it up here, give it a default value. Question now is whether that will be allowed, whether that variable is in scope for that one. Let's see. I think we'll be able to see when we just run it like that. Okay, so it worked at that point. So I'm gonna imagine that means it's worth pushing and testing on CI. So let's see, and let's see if we need to do the same thing on the other file as well. Is the packages variable reference before it's defined? No, it's the first time it's used is there, and it's defined there. Okay, so let's push that upstream again. And then we'll come over here and we'll ask it to please evaluate again. And then we'll see whether that works, whether we have any more luck with that. So now it's going to go off to GitHub and fetch the latest code and run that. Evaluation is now running. So what evaluation means for Hydra is it's downloaded all of the inputs and it's running the Nix code to figure out what needs to be built. So which benchmarks it needs to run, and then what the dependencies are, which reports it needs to generate, what benchmarks that those need to import results from, and then to just get everything running. And this Hydra has a bunch of machines. So if we just look here, it's got the local host. It has a server called Grindelwald. Grindelwald is a little bit special. It has special hardware which is useful for some of the snap tests. Specifically, it's got 24 CPU cores, and it's got 20 10 gigabit Intel network cards. So it's really nice if you want to have a machine where you can test 200 gigabits per second of networking with a separate CPU core and separate 10 gigabit port paired up. Then that's where we do that. It's a handy server to have. We also have our Lugano servers, 4 of those. Those are all smaller identical servers, identical CPUs, and a little bit of difference in hardware. There we have some other mixed network cards. We have 100 gig Mellanox cards, that kind of stuff. And the Murin servers are where we're going to run these tests now. This is the generic compute that the CI has available. We have 10 servers at Hetzner, which are only used by the CI. So the nice thing about those for benchmarking is we know that when the CI goes and runs a benchmark there was nothing else going on the machine at that time. What that means is that when we see kind of fuzz and variation in the benchmark results, it should be coming from something interesting and not something boring. Interesting would be something that we can address in our software. Something in the way that the runtime system works, for example. And boring would be if we were running this on if you're running the benchmarks on Travis CI or something, and they were running it on a busy, over-provisioned cloud host, then it might be that we would see a lot of variation that was nothing to do with our software. It was just about the execution environment, and then it would create work for us. We'd have to account for that somehow. Anyway, with that digression out of the way, let's see whether the evaluation is finished over here. Yes, that's nice. So what is it going to build? What are the jobs? It's going to build benchmark results. So just because of the way that I wrote this script, it's just not going to be all that visible. I told it to build just benchmark results. So we only see one job here. It would be kind of nice if it actually listed each individual benchmark separately, and then we could see everything that it's planning to build, everything that's going to reuse from a previous build, everything that failed to build, and so on. So while that's running now, we might just actually update the script to work that way. So when we this is the Nix expression. This is a Nix source file that says how to run the benchmarks suite. It finishes off by returning a set of things that should be built, and that set currently contains just one thing, which is called benchmark results, and indirectly that references over here benchmarks for branch A, B, C, D, E, and so on. So even though it only returns one thing to build, as a dependency, it causes everything else to be built, but that's kind of invisible in the background. But maybe it would be nice if that was not invisible, but it was rather visible. So let's just see if we can put all the individual benchmarks into that set as well. What format do we have them in? So this, this is the question is whether I need to do any refactoring here. So I need to put them into this set at the end. I need to merge some other sets. Things. It's basically like a dictionary. You'll have some keys and values, and I might have to do a little bit of work to just massage the benchmark list into a benchmark set in the right format. And when you're live coding, you get stupid rays getting blasted out for the webcam. So maybe right now I'll save that for later. It's probably just a map and a fold and that kind of thing. But let's do something else now. Okay, so the CI is still working on those. We don't see what it's doing directly, although we can kind of indirectly see a little bit. Here's the build. Oh no, okay, I tell a lie. We can get reasonable visibility actually. If we look at the build steps, there we can see this was the first set. So the first set of benchmarks and the second set and the third step for the next branch, they're all running in parallel. You see the name of the machine that's running it. We're in 724. We can tail the log while it's running. So there we see the progress of running those benchmarks. So actually I underestimate Hydra. It's actually pretty transparent what's going on in the build, even without taking special precautions, which is something nice that I learned today. And we can see it's treating everything in the same way. So it's got to run benchmarks. So this build step is actually running some benchmarks with RaptorJIT, and so is this, and so is this. Whereas this one is actually getting some software. That's getting the ggplot library for R, which might get built or might get downloaded from a binary cache, and getting all of these other dependencies that are needed. So so this is actually kind of what I like about Nix, that if you want to be able to use tools like R, then they got a lot of, they're big ecosystems. They have a lot of dependencies of their own, and I just don't want to be exposed to the randomness of things getting updated and software packages changing and combinations changing and dependency hell. So the thing here is that Nix goes off and it gets exactly the same version of these, or exactly the version that was specified in the package tree that I referenced by git commit. So it always gets exactly the same version of these. It always builds them with exactly the same version of GCC, with exactly the same flags, using exactly the same glibc and everything. So it just takes away a whole dimension of dependency hell problems that I would have otherwise. So I would not, if I didn't have Nix, I wouldn't be using R for this, because it would just be too much of a pain, way too much of a pain. So I would be, I'd be doing ASCII art with awk or something like that instead, because I just wouldn't want to deal with the dependencies. So I think Nix is really cool. It's opened up a lot of more software to be palatable for me. So rant. Let's refresh this and see where we are. A lot of stuff has succeeded. Okay, that all succeeded. Aha! Success. So this is, for the very first time, the CI successfully running the benchmarks and publishing the results. So we can get the details. We can see for the inputs, we can see exactly which versions it ran by git commit, which is nice, and exactly which software dependencies it used by git commit. So there's a lot of value actually in just running things on a CI, so that you have this audit trail. But then from there we can get a big summary. If we click on that, wow, cool. Now in the browser, it's very large. Shrink it down slightly. That's our graph. It's only done 3 tests, 3 runs of each benchmark. We have, I don't remember if it was 25 benchmarks or something. So in total it's only a couple of 100 tests or something. That's why the confidence bands are so wide. But this is kind of neat. This is the CI fully automated, generating that big report. So I'm going to use this constantly now. Very nice. So with that having worked, let's do we'll go on to something else. But while we do, we'll kick off a bigger run here. Just to see what the report looks like when we have more data. And for that, we want to go back, click our way back to the definition of the job. Go via the other interface. And we will, in the configuration, we said 3 runs of each benchmark with each branch, but let's live a little and make that 100. And this is a kind of a nice thing. So we have a bunch of servers there. We have Hydra that can schedule things and prioritize things. So now that this is defined, it's going to be polling all the time the GitHub for the master and the next branches, and if either of those branches changes, it's going to automatically kick off a benchmark that by the time we're interested in seeing the results, that it'll probably already be there and ready, which is really nice. So that evaluation is running, so that's started doing its thing, and we'll come back to that later. Meanwhile, we'll go to the next things on our list for the morning. We have set things up to run on Hydra. We have imported Nix packages in a compatible way. We have configured a Hydra job set. Okay, one more thing I want to do with Hydra, but we can take later, is in this instance, it's testing the master branch versus the next branch. So this is kind of for release candidate testing, you might say. It's to tell us whether the development branch is in a fit state for merging onto the master branch, which would represent a release. But what I would also like to do is be able to do kind of ad hoc testing with experimental changes. And of course, I can do that on my own local machine, and maybe that's what I normally will do. But it would also be neat to have a job set that compares the master branch with the next branch with also my own development branch. So I can just set that up with a third software version. Hydra actually will do a really nice job of reusing any benchmarks that haven't changed. So if I have several job sets that are all running benchmarks of the master branch, for example, then under the hood, Hydra will see that they're testing exactly the same software version with exactly the same dependency versions, and it'll just run the test once and then reuse them. So I can actually define a lot of different jobs, and what will actually execute is kind of the union of those. It will not redo everything separately. So the incremental cost of a new benchmark is pretty modest, which is really nice. But what we're going to do now is take a 5-minute break and then have a look into that that problem that was there. So if I just hop back up for a moment, in the first graph we looked at, there was this gap representing some benchmark running slower on the one version than the other. We had a quick look at that yesterday, but I'm going to just have a proper look at that. So it might be interesting. It was very surprising, and we did a git bisect. It identified a commit as introducing a regression on that benchmark, and just glancing at the commit, it didn't make any sense to me why that would be a problem. So we're going to find out, get to the bottom of that in 5 minutes. So hopping back on, Hydra is off running our benchmarks for us. It's going to build us a nice report, and while it does that, we're going to look into why one specific benchmark has slowed down a lot in the latest version of RaptorJIT compared with an older version. I hadn't been doing automatic testing of the benchmarking on the intervening versions, so we need to figure out what caused the slowdown and then fix that. And we already did a git bisect yesterday to find the commit that is where the performance flipped down to be slower, and this was the commit ID, and I was kind of surprised because it didn't look like anything that should impact performance. So now we're going to get to the bottom of that. So to do that, we will hop into a RaptorJIT source tree. We will check out we'll just see where we are. So we'll check out the latest version first. We'll do this in another working tree. So not the normal Git workflow, but just to avoid any surprises today. We'll hop into that directory. We will build the JIT, and what we're expecting is, based on our notes, what we're expecting is that when we run the life benchmark, it will take about 8.6 billion cycles to complete, and we will. This is longer than it used to take in the past, so we're going to look into why that would be. So now we've built the JIT, and we will run source RaptorJIT on test suite benchmarks life, and we will perf stat that to get the cycle count. $8.6 billion cycles, so that was basically as expected. And then if we just manually test the other relevant versions, Git has told us that this version was the first bad one. We did a git bisect, so let's check that ourselves. Build this. And run that. So what we're expecting is the same performance again. This is with an older version, which we think is the first bad version, okay? About 8.6 billion cycles again. Now if we check out the previous version, see which commit this is as well. It's where we introduced the size of IR machine code tracking. We'll come back to that. First, we just double check. We go back to the previous commit before this and just make sure that had better performance. What we're expecting now, when we step back one revision, is that the performance will be a little better. Yeah, 6.7 billion cycles as opposed to 8.6 billion cycles. So somehow that change has been a problem. Okay, so if we now go back where we were, and if we this is the diff of the change that seems to have caused a problem. So, so this is really surprising to me, because all that this change does is when the JIT compiles code, there's a struct GC trace, which is the structure representing compiled a trace of compiled code. We add an array of size fields. So for each IR, intermediate representation instruction, we now keep track of how many machine code instructions machine code instructions were assembled for that IR instruction. So the point of this is to be able to create a mapping later on in development tools that when we want to see the correspondence between an IR instruction and one or more, zero or more machine code instructions that it assembled into, that we'll have the information to build that. So it uses a little bit of extra memory. Of course, there are a lot of ways on a modern CPU that adding a bit of memory somewhere can impact performance. I will be surprised. Well, I'm curious. I don't know what's going to be the reason here. So what I would like to do now is I would like to try just taking this change and backing it out on the latest version, so that then we're testing the latest version, but with that change removed, to see if that helps. Now that's a merge commit, so we need to think about what the right way is to do a git revert on that change. That's the change that was flagged, but it's a merge, so I will need to practice my git foo a little bit. If we check out the master, and then let's call this working branch life debug. And can you revert a merge commit like that? And if so, what happens? You need to give it -m, so I think we need to tell it which parent of the merge we want to revert. Is that index from 0 or 1 is my question. I think it's from 1, but let's just double check. Let's try actually and see if we get what we want. Git revert, second parent. Got a conflict. That's possibly the wrong one. Let's try the other parents. Maybe it's telling us which one we want to keep. Okay, my git foo is a bit weak for this today. I'm sure it's the stupid rays coming out of the webcam. Let's do this instead. Whoops, we will do. Oh. So what I really want to do right now is I want to extract this one specific change to make sure that it really is that change that's causing the problem, and that I'm not misinterpreting the Git history somehow, which is always a risk, right? We're dealing with merge commits, so it's possible that when I've bisected, it's told me this commit is to blame, but that actually I'm misunderstanding what the relevant content is. So I'm going to pull out the code that seems to be causing the problem. I'm going to patch that on and see if that fixes the problem. If it does, then we know certainly that that's the issue, and otherwise we can have a little bit of a closer look. So we're going to just search for the size. So I think it's actually this commit. Once you eliminate all the merges, that should be the issue. So I'm going to just see if I revert that. Okay. Finally, now we have the master version of RaptorJIT with this specific change reverted, and we're going to see whether this has the fast performance or the slow performance. So if this has the slow performance, then that change was the problem. If it has the fast performance, then I've apparently misinterpreted the result of git bisect. I need to look again at that more closely. Here we are running the benchmark. That has the faster performance. Okay. So it really truly is that change. I haven't misunderstood git bisect. It has identified that kind of diff, as being where the problem was introduced, and if we take that specific change out of the Git history and revert it on the tip of the master branch, then things get nice again. So I mean, if one thing that we could do is just revert this and push that to put performance back as it's supposed to be while we dig in. We'll try to fix the root problem first, because this is actually pretty interesting. This is actually really cool to have such an interesting example, a change that doesn't seem like it should impact performance, but clearly does. And we'll spend a little bit of time trying to get to the bottom of that, and with the backup plan being to just back it out, because it's adding debug information that's not actually being used yet. And so if it wasn't ready for merge, then it didn't really need to be on the trunk. So let us do this in Emacs shells, which I find a little bit easier to deal with than Tmux. So we're going to want to let us take the build that we have now, which is the faster one, and call this and then let us build from the master version again. So we have, we're going to just have this kind of a split screen. On the one side we have the one that's running fast, and the other one we have the one that's running slow, and we'll just do some happy testing comparisons between them to see what interesting thing that we can see. So now the build that we have should be the slow one. So now what I expect to be able to do is say that's kind of interesting as well. This generates a lot of output. I don't know if it's going to be valid to do this in. Yes, it is. It's generating a lot of output, so in principle this performance could be limited by the terminal that it's printing to, and then running it in Emacs could actually change the result of the benchmark. Didn't seem to happen that time. We got about nearly 8.6 billion cycles with the one that we flagged as slow, and now if we try the one that we flagged as fast. So the first thing that we're actually going to do is compare some of these other numbers. We've compared the cycles. Now we'll see something else. Okay. So the slow binary did give us around 8.6 billion cycles. The fast one did give us around 6.6. So we are seeing the performance difference. What else can we see here? Well, one thing we see is that there was also a corresponding increase in the number of instructions that were executed. There were kind of two basic explanations for why it could slow down. One could be that it's doing more work. The other could be that it's doing the same work but more slowly. So since this change is moving things around in memory, if it had, for example, pushed a lot of data structures onto 4096 byte alignment, then they could be colliding in cache lines, and we might not have to execute any more instructions. It might just be that the same instructions are kind of pushing their workload against each other and slowing down. But anyway, that's not what's happening. So we see that the slow one is actually running more instructions per cycle than the fast one. So the problem is that for whatever reason it's doing more work. It's running more instructions. And the next interesting question there will be to know where is that work being done? Is this JIT machine code, or is this somewhere else? Is this in the terminal code in the runtime system I/O that's doing this printing, or what? Very interesting. So let's pop out for a second and actually. It's interesting as well. I've been doing a lot of work on profiling tools for the Lua level of things, but in this case this is very unlike the kind of performance things that I usually deal with, in the sense that this is there's a lot of system calls involved. In Snap we don't make any system calls really, whereas here there's some I/O going on, so it's entirely possible that the issue here can have nothing to do with JIT code. On the other hand, it might. I'm going to do Just try hitting them with perf a little bit, and maybe it will actually make sense to switch away from Emacs here and actually have two separate terminals. Let's try that. Because perf is going to want to do a little bit of ANSI escape graphics, and it's not necessarily going to be happy inside Emacs for doing that. So we'll give it its own little environment. So instead of running just perf stat, we'll do perf record. Okay, that's just an overview of what was being done in the slow version from the perf level. The thing that jumps out here is this is all runtime system stuff. It's creating intern Lua strings. It's doing allocate and free in the runtime system. It's resizing strings. It's sweeping the garbage collector. It's calling into the libc to a memcopy. So this is not this is runtime system code. It's not JIT code. So this is it is interesting. Anyway, let's just hop in and see how that compares with the other one. So actually, I'm not using perf every day because, as I said, in Snub we basically don't do system calls, and we basically spend all of our time in JIT machine code, and so this view is actually seldom very relevant because the Snub software is mostly running in generated JIT code. Perf can't see the contents of the JIT code, so with that disclaimer out of the way, I'm a little rusty on my perf foo. So let's hop in. Look. I could give it a different file name. I just run it from a different directory. Perf record. Run the fast binary now on test suite benchmark live. See the report there. So what is different? And again, I suppose I think the perf has a feature for doing diffs on these things more directly. So I'm a bit of a caveman here to be actually pulling them up side by side, but we'll see if we can get to the bottom of things anyway. So allocating strings, we're spending more time doing string allocation. Everything is relative. More time doing string allocation in the new one than in the old one. So actually, you know, this is a case where it would be nicer to see raw sample counts rather than percentages. Actually, what I would like to know is how many samples were in each of these. So I got to have a look then to see if we can ask perf to give that. Because the thing is that I want to be able to compare from two different runs here, and I should be able to compare the samples, the number of samples, kind of apples to apples, supposing the perf is sampling at a more or less constant rate. But the percentages are kind of only valid within a process. So there ought to be a setting to see samples instead of percentages. Which I don't see. It must be possible. The number of samples, so minus n. Let's try that. That's more like it. Now we have a column with the number of samples. Okay, this is actually starting to look kind of useful. So we see on the string u, we see that on the binary that performed poorly, we got 10,000 profiler samples. On the one that worked better, we got 6,800 profiler samples. I'm kind of assuming now that perf is sampling at a constant rate, which certainly seems to be, given the total sample count. Got 11,000 samples for the fast one and 14,000 for the slow one. So if I'm wrong about that, I'll be talking nonsense now, but it seems a reasonably safe assumption. Then looking down at the other ones, we see free got a more similar number of samples in both cases, 1,200, 1,100. malloc also a similar number. So it really looks like somehow this change has caused string allocation to slow down. It really looks that way. So LJ stir new is the function that is spending more time after we introduce that change. And if we just have a look at the change again, just for the sake of clarity, all it's really is, it doesn't deal with strings at all. It's when the JIT generates new machine code, a new trace of machine code. It allocates a little bit of extra memory in the struct GC trace where it can put some extra debug information, which is this array saying for each intermediate representation instruction how many bytes of machine code were assembled, so that we can create a mapping back and forth between an IR code and M code. Cool. So I think the next thing then is to actually look in the source code for I wish that my window was a little bigger now. I can probably get away with this, having one window. Now we're going to want to look in the source code for that string function and see why is it bothered. You know, is for some reason does having another allocation somewhere else completely screw that up? Very interesting. So if we look in the source and LJ stir.c, we'll assume it's called. Well, and I guess what I'm neglecting is that perf can actually hop in here and probably tell me a little bit more. Hold on. We get sample count there. Look like it. Okay. May have compiled without debug information. I wonder if that's why it's not giving me source code. It's only giving me assembly. But anyway, let's read the source code first of all and see if anything jumps out at us here. So how much code are we looking at here? About 2 pages of code. I will narrow this in Emacs to make it easier to stay in bounds. So when we create a new string, if the string is too big, we error. Otherwise, we find we use the Lua state to get to the global common state. So every string, every Lua string is interned. So when we create a string, it's immutable and it's stored in a hash table, so that if we come along later and create another string with the same contents, then they will be the same object. So it's like a symbol in another language. So we compute a hash, which is special cased for empty strings. We bail out if it's an empty string. Otherwise, check if a string has already been interned. So okay, and so this is interesting as well. So I'm maintaining RaptorJIT, so it's my job to fix this. I'm the maintainer of this software. But at the same time, it's a fork of LuaJIT, and Mike Paul developed LuaJIT for like 12 years or something before I ever started doing my maintaining. So I've never seen this code before. So every time I do some work on RaptorJIT, I learn a little bit more about the code base, and gradually, I'm maybe halfway there now in terms of coverage of actually understanding basically what is going on in each part of the system. So I've never looked into the string allocation, string interning code before, so I'm reading this code for the first time. But the next time there's an issue with string allocation, I won't be, and so that's why it's worth my time to spend here, because I'm intending to maintain RaptorJIT for a long time, because it's cool. Okay, so has the string already been interned? Slow path, end of string is too close to a page boundary. That certainly sounds interesting. What do we have here? If the string address plus the length minus 1, end of the string, masked with LJ page size is less than or equal to the page size minus 4. This seems so incredibly specific. So it's checking whether the end of the string is going to be closely aligned with a page in memory. Let's check what the page size is. I assume it's 4K if we're talking about CPU pages. Yeah, okay. All right. Let's see why this is important. If the end of the string is below this, sorry, this is the fast path, this first branch. If the end of the string's alignment compared with the end of the page is far away, if the string is not right close within 4 bytes of the end of the page, then this is what we do, the fast path. And so then what is the difference here? Why is this fast path faster? What's the difference? So let's use some poor man diffing here. 2 windows on that buffer. But on the right hand side we'll have the slow path, and on the left hand side we'll have the fast path, just so that we can see what's the issue. We'll begin on the while. Okay, so this is the fast code, and this is the slow code. So what the hell? While O is non-null is the same on both. GC object to string is the same on both. Here we have a difference. Okay, so if the string that we're looking at has the same length and we do a string fast comparison, otherwise we do a mem compare. So we have a string called string fast compare, and we have a call to presumably the libc mem compare. And for some reason, if the string is close, if the end of the string is closely aligned with the page barrier, we will not call the fast compare. We will instead call the standard or some default memcompare function. Any other differences? Is dead, flip white, is dead, flip white, return SX? No. Fascinating. So we have two ways to compare strings. One that's fast that we use depending on this alignment. Okay, so anyone watching this maybe knows exactly, obviously, what's the reason for this. I've got no idea whatsoever, but obviously we're going to look at the definition of these functions and try to understand why is the fast compare faster and also restricted to not work with strings whose ends are closely aligned with the page boundary. So we'll do a little grep. Fast string comparison. And okay, before I dive into that, I actually want to see also whether it's the glibc memcompare. Maybe we can even see that over here. What is our baseline, our slow path? Is it the memcompare that comes with libc, which is absolutely going to be some crazy, funky assembler code written by somebody at Intel, or is it something some other one? So that we should be able to see in the perf report for the slow one. I just want to see in perf. I want to see somewhere here. Okay, it was here. No, that's a memory copy. So we're looking for a memory compare. Okay, but whatever it is, because perf sampled it into this LJ stir new, so that memcompare that runs slowly, that has presumably been inline because the profiler is not pointing to a libc function, which is interesting. So it might be a memcompare that is written here in the code base that I haven't seen yet, inherited from RaptorJIT. It might be a slow path memcompare. It might also be code that GCC, that the C compiler has put in. It's seen a memcopy and said that it thinks it knows how to do that itself, and or it might be a call to libc. I don't. Well, we can see there's not a call to libc actually from the profiler. Anyway, fascinating. Let's just check if it might. Let's see how our memcompare is defined. Our baseline so-called slow path memcompare. Oops, one of the kids has hurt himself in the next room. Poor little fella. Give me 1 second. It's really nice having the kids playing in the background in the home office. I love it. Anyway, so memcompare doesn't look like we've defined our own memcompare anywhere. It kind of looks like we're using whatever is provided by the compiler. I'm going to be interested to dig into that later, perhaps. Anyway, first of all, let's take a closer look at this so-called fast path. String fast compare seems to run fast and seems to have a strange restriction with alignment, if I understood correctly. Okay. So, it's always fetching. Sorry, I'm getting ahead of myself. So I think the thing with this string comparison function is that it is always fetching 32 bits at a time, which incidentally is not very much. We could be doing in RaptorJIT we're only targeting 64-bit machines, so actually we could be doing 64-bit here, which would probably be faster and might be worth doing, but anyway, that's not the topic now. So it's always fetching large words. It's always fetching 32 bits at a time, so there's always the possibility that it's going to read a little bit more data from memory. Oh. What are you after, buddy? I'm just looking at the eggs. You're looking for eggs? Where's the egg go? Daddy, where did the eggs go? I have to attend to something. I'll be back in only a couple of minutes. So, you know, co-working spaces.
Daddy,
Yes, Brad.
Daddy, they get these out. These comes a Harvey.
You need to take those ones out?
Yes, these are Harvey.
Hey, but Fred, Daddy's working.
Daddy, from some of these paints.
Do you want these paints?
Yes.
You want these paints? Okay, hold on. I'll get you the paints.
These are also pink.
There you go, buddy.
Thanks.
No problem. So I misplaced the lock for my office door. So this is my reality is occasionally providing some assistance and supplies to the little fellas when they need them. You know. Anyway. So what we would do? Okay, so I was having this aha moment with the fast comparison. Okay, so generally speaking, if you wanna do fast comparisons, it's much quicker not to load a byte all the time, but rather to load words. You know, because the CPU is just as happy to compare 64 bits as it is to compare 8 bits on a single instruction. So what we have here is apparently a special case comparison that always loads 32 bits at a time, which later we're going to come back and consider expanding to 64 if this function survives this sojourn. But of course, if you're always fetching extra data and you're not doing a check for the end of the string, you're not special casing the end of the string particularly, then there's always the risk that you read some bytes that are not really a part of the string, and there's this kind of hardware-aware optimization here that says you can't do that if you don't know about the allocation of your memory. So if there is the possibility of a string, if there's possibility that the memory after the string is not mapped in your process, then you're going to get a seg fault, right? So if you would have a right. So it's accessing the string with unaligned reads. So it's entirely possible that to get the last byte of the string, if the last byte of the string is on the last byte of a page, and the beginning of the string is, you know, unaligned by 3, then when we load the last byte of the string, we're also going to get the 3 bytes from the next page, and that's going to be a seg fault if the memory allocator happens to have oh, this is so cool, you know. If the memory allocator happens to have allocated the string in a block of memory that, you know, where the following addresses are not mapped. So it's just so amazing to me that I've done an allocation in a completely, totally, absolutely different part of the system, and it has genuinely slowed down string interning, because somehow it would seem strings are now much more frequently having their ends aligned with the end of a page. Totally amazing. Totally amazing. So what are we going to do? So I want to. So I don't like this kind of optimization for a couple of reasons. One is it's just kind of complicated. Well, no, because it's complicated. Well, and also because it's a little bit fragile, right? So this code only applies in very specific situations. It's a very broad situation in principle, but it's hard to really say how frequently string ends are going to be aligned with page boundaries, and this kind of exposes me to these kind of problems. You know, that I do an allocation somewhere else, it happens to affect the alignment of string ends, and that happens to cripple my performance. That's I don't know, that annoys me. So what I would like to do now is I would like to preserve the performance, or even improve it. I don't want to go backwards, but I would also really like to have a single implementation, a single code path for everything, rather than having these two cases, the fast path and the slow path, because then I got to worry about whether any change anywhere that affects memory allocation is going to be bumping something into the slow path, which might be incredibly unobvious. I'm surprised it happened now when you consider that, you know, page is 4K. And it does seem a little bit funny that so many strings are suddenly having their ends aligned with the page boundary. But anyway, I don't want to be exposed to that class of errors at all. So let's think about what we could do here. So the first thing that jumps into my mind is that when we allocate a string, we could just pad the memory allocation a little bit. We could just allocate you know, 3 extra bytes at the end of the string, so that we're always allowed to overread a string by 3 bytes, because we know that the memory is allocated and mapped. Why not? Let's see if that's a way, if that's something that we could do. And the nice thing about doing that is that we wouldn't have to use the slow path anymore. We could always use this. We could always use this fast path. And then if this works, it would be kind of neat for bonus points. We could then try switching the fast path from using 32-bit comparisons to 64-bit. It would be kind of nice, potentially. So LJ string new. So if we want to allocate a little bit of padding at the end of our strings, it's probably going to be easy, provided we're not doing the allocations in too many places. So I'm hoping that this is actually the only place that we do it. Maybe we will update this function and have to separately do an audit to make sure that there's no other ways that strings come into the system, such that we are not really establishing our invariant that strings are always padded on the tail. So where do we allocate memory for a string? It should be somewhere in this function, which is the LJ string here. So when we allocate a string, memory we allocate is for the object header for a string plus the length of the payload plus 1 byte. Okay. So call me silly, but what if, just for a preliminary hack, if we change that 1 to a 4, so that we always have an extra 3 bytes at the end of our string, and then we just always use the fast path, because we can always overread a string by up to 3 bytes. So then we delete some code, which I love to do. Slow path doesn't exist anymore. Don't have to do this check. Don't have to. There's a certain irony as well, that in this C code there's a static annotation telling the C compiler that please optimize for the case of the fast path, because that's the most likely. So it's kind of amusing then when we run a benchmark and this is not actually turning out to be likely in practice, and not only are we falling back to the fast path, but we've also kind of told the C compiler to not optimize the slow path as well. I don't think these annotations actually have any significant effect, but anyway. That goes away. This is the only code that we have. Let's run that, see if it works. Check first, were we on? Yeah, we were on the master branch. That should be slow. Let's just build and check. Oops. Oops, a syntax error. What have I done wrong? How are we running this? Life. So if this takes, I can't race the benchmark. I won't try. Oh, okay, no, we can. So okay, that was with perf record. We're going to run this with perf stat. So that's how we do our health check. Remember, we say tell us how many cycles this benchmark took. If it takes 8.6 billion cycles, then we expect then that's considered slow, and we think that's the problem case where we're taking the slow path on string allocation of all things. If it takes around 6.6 billion cycles, then that corresponds with the case where it's taking usually the fast path. So now I hope this is going to say 6.6 billion cycles, because everything should be on the fast path now. Let us see. Wow, that was super slow, super duper slow. No, wait, yes, 14 billion. So that totally threw performance completely out the window. How interesting. So again, so 14 billion, if we ran with the fast version, just to make sure we're not hallucinating. Yeah, okay. So that was a massively unsuccessful attempt. Massively unsuccessful attempt to optimize that. So probably I've missed something crucial. Well, okay, I think I have. I think when I clipped that code, I was in such a fit of enthusiasm that I possibly. Oh, wait, let's have a look. The code that I removed was this slow path and this check here. Okay, but that seems okay to me. I don't see the problem there. So I'm surprised that this is running slowly. Let me just check it again, just to make sure I'm not hallucinating. So is this really going to take 14 billion cycles to run? Oh, sorry, I ran the wrong binary, I'm sure, yes. Sorry, is this really going to take 14 billion cycles to run, or was that a fluke, or was there something funny going on? Yeah, it does. Okay, so I've massively degraded the performance with that change. Very interesting. I have no idea why. If anybody is seeing this over my shoulder, please leave a comment on the YouTube chat, or write something on Twitter. Otherwise, I'll struggle along, and you can enjoy watching me sweat. So, I'm gonna have to have a little bit of a closer look at whether there was anything else going on here. Hang on. No. Put it back as it was. So was there really some major consequence to removing this? We already looked at this and decided that the only difference was in the memory comparison. It should always enter the while loop, because it's either this if matches, otherwise that else does. It should always go into a while loop. It should always reverse its way through. It's looping through objects in the heap. I think we probably need to profile this again as well, because if you think that the whole problem we had is that we changed the size of an allocation in one part of a program, and then in a completely different part of the program we got some totally unexpected performance problem based on the way memory was now being aligned. Now we've changed the memory allocation in this part of the program, and maybe there is yet a third part that's totally blown away. So actually we should probably profile this again and see whether this change that I made actually failed to solve the problem, or whether it actually successfully solved the problem and in doing so introduced an even bigger other similar but different problem. That would be kind of amusing. Okay, and we'll continue to sweat. Here we are with our code. We are now always taking the fast path, always using the string comparison function that is only safe when you know that there are at least 3 bytes of valid memory after the string. We are, when we allocate memory for a string, we're always putting our extra 3 bytes. It used to be a +1, now it's +4. Hold on a second. And that's me distributing paintbrushes. Yeah, so let's just run this and profile it. I'll stop yabbering and we'll build. We'll do a make clean to protect ourselves from witchcraft, and because we have plenty of cores for compiling with. We'll run the benchmark using the current binary, expecting to see this very slow 14 billion cycle result. Yes, and now we'll do a perf record on that and see what the profiler says and see how that compares. You know, here we have the original fast version, and now we're going to have a look here. See how that compares. So, in the olden days version that had the performance we wanted, the string new function on this benchmark got about 10,000 profiler samples. Now it's getting about 20,000 profiler samples. So what that tells us is that this fix has backfired. So that it's not that we solved that problem and created a new one. It's that this specific function, ljStringNew, is running worse than it did in either of the other 2 versions. And if we just sanity check a little bit the other functions, allocate free was about 1,000. Yeah, it's still pretty similar. So it really looks like the only difference, as far as the profiler is concerned, is in the string allocation function that we've been hacking. So basically, what it means is I did something wrong in that fix. I have no idea what it is yet, but somehow this, 2 pages of C code that we have in front of us was much faster before and is now going much slower. I'm just going to do that same comparison that we did earlier and just double check with perfstat. Is it that we're executing more instructions, or is it the instructions we're executing are going more slowly? Oops, and I should take away that. So before we had about 2.1 to 2.3 instructions retired per cycle. What do we have now? 2.2. So okay, we're doing more work than we did before. Wow, okay, so this function has slowed down a whole lot as a result of my tweaking it to always take the fast path and never take the slow path. This is surely something very silly that I've done. It will be lovely to watch this again and see what I'm overlooking. Let's take this again and let's read the diff to start with. Make sure that that's the only things that we're changing. In the old version, let's do a nicer diff. It's a little small. Why on earth would it be a problem in that case? Hang on. Aha. I screwed up. That's the good news is, no, hey, wait. Is it just grayed out and I'm not seeing it? Oh, okay, no, sorry. This is counterproductive. The edif, I usually run it in native windowing with nicer colors, but it's actually just obscuring what's going on there. Let us instead just put the current version and the original version side by side. That on the left is the original version. Let's do it the other way around. On the right hand side, we have the original code, and on the left hand side, we have the new code. So this is the optional fast path in the original code, and it's always that way in this code. So while the object is non-null, so while we're still finding strings to traverse through, the string that we find has the same length and the same contents as the string we're returning, presumably. Then we check it's dead, then we flip the white bit, the garbage collector, which was the same on both the fast path and the slow path, so that should not be affected. And we return it. Okay, so we're looking for. So I guess that we are traversing a hash chain of strings that all have the same hash value. Yeah. And if we find one that has not only the same hash value but the same length and the same contents, then instead of allocating a new string, we're going to return that string. So the loop that we are optimizing, or really rather pessimizing, is the one where we have a string that we want to turn into a Lua string. We've calculated the hash value, and we just want to know, do we already have this string on the heap somewhere? And if so, we'll return a reference to that. Otherwise, we need to allocate a new one. So it is that search for a string that actually has the same contents that is slowing down. Okay, I'm just going to have to change something. I need more data. So what about if we make this always run the slow path, just for fun? Can't make this program any slower than I already have, right? Let's see. Let's build that and run the benchmark and have a look. So and it looks like it's running slowly. Oh, 10 billion cycles. Okay, so if I if I change the program to always take the slow path, then that slows it down. If I change it to always take the fast path, then that slows it down even more. So let's have another look at this function. Maybe there's something going on there that we need to think about. We'll call the call to the fast path back. So why on earth would this function run differently? So first of all, we don't have big endian support in RaptorJIT at the moment. So I'm surprised I haven't already removed that ifdef. Anyway, what can it be about this code? No, okay, so there is actually an assertion there which we haven't removed. Again, the change that I made to try and make the fast path always valid is to always allocate a little bit of extra padding data at the end of strings, and that should mean that the fast string comparison function can always be used, because it can depend on being able to read always word size data and never cross the page boundary and access unmapped memory and get a seg fault. So we're not running with assertions, but even so, we should remove that, because otherwise it would potentially fail, because there's not a requirement anymore. And while we're here, we will remove the big endian support. I think that we will support big endian machines in RaptorJIT in the future, but that's the future. Today we're only targeting x86 and we want to focus all of our brain cycles on making the best x86 JIT that we can. But they can then later be updated to support, you know, other architectures. But for now, there's no place for big endian code in RaptorJIT. Okay, so we do a loop. We pull a value, a 32-bit value. So okay, so we're looping starting from index 0, and we're bumping the loop by 4 bytes every time. So we consume 4 bytes every time. The way that we consume it is that we do get u32, which is presumably an array access. We'll need to check from the base of the string plus the index that we're looking at. And then, sorry, we're doing a string comparison. In string comparison, we have string A and string B. Okay. I wonder why it's written in this way. So string A we access using this special macro or function. String B we access with a normal pointer dereference. And rather than doing an equality check, we do an XOR of them and check if that is 0, which I guess is maybe trying to hint to the compiler that we don't want to branch. No, I don't even know if that's a reasonable explanation. So if oh dear, it's interesting having code like this to internalize. As a software maintainer, I see this as a real cost. When you write a clever function like this, if I go to the RaptorJIT homepage, sorry, pardon me ranting. You know, I'm espousing the RaptorJIT philosophy here. One of the things I collected some quotes about. Oh, hold on. So yeah, when I started working on RaptorJIT, I collected some quotes, you know, as you do in the early days of projects when you're being very self-indulgent. But partly the idea of this is to kind of, in my own mind, clarify the way that I like to write software, in contrast to the way some things are done in LuaJIT. You know, LuaJIT, it always feels like there's an embracing of complexity. So if you have a really super clever way of doing things, then you do that and you're really happy with it. And I think that that's been a very valuable part of the project, in the sense that Mike Paul is a really clever guy. He really enjoys, you know, formulating clever solutions to problems, and LuaJIT has been a vehicle for that. So the whole reason that the project exists is that it's given him a creative outlet to do his really kind of clever programming. I'm different, right? I'm an application programmer. I want Snap to work as well as possible. That means I need the JIT to be as predictable and simple and obvious as possible, and to not take too much effort to maintain, because all of the effort that you have to spend digging into the JIT and the runtime system is effort that you're not spending on your application. So I was thinking of the illustrious Dijkstra saying that, among other things, the competent programmer avoids clever tricks like the plague. Anyway, so what I was kind of thinking there is, for every clever trick in the source code, somebody coming along someday is going to have to sit there scratching their head figuring out what the code is. And I've got the stupid raise from the webcam coming, so you know, it's going to take me a scandalously long time to solve this problem. Anyway, I want to see what this get u32 macro is first. The first thing I want to know is just to tease this out. We have two strings and we're accessing the contents of them in different ways. For first string we're doing this, and the second string we're doing just a pointer dereference. So what the hell is this? Most units and header file. Interesting. So, so I mentioned earlier that RaptorJIT for the moment is only targeting 64-bit x86 processors, and particularly we're optimizing for Intel processors, which hopefully indirectly means we also optimize for AMD, since they don't have the luxury of being able to have two different microarchitectures, I don't think. Anyway, unlined access is not relevant on these x86 Intel CPUs. They can for normal integer instructions they don't care about alignment, neither from a performance perspective or from a kind of a functional perspective. So you can access memory on any alignment with perfectly good performance. So it's a little bit. I don't immediately know why we care about alignment there, and I also don't immediately know why we care about it only on one of our operands. So why? You know what? What if we just... So we've already seen that the libc function actually did run slower. This slow path that called out to libc to do a memcompare actually did run slower, and I suspect that it was not actually libc, because we didn't see libc anywhere in the perf profile. So I suspect actually that GCC saw it was a memcompare and decided that it thinks it's better at compiling memcompares than libraries, and probably GCC actually just inlined from its own memory a string comparison function. So, but I don't like this fast one. I don't want to switch everything over to this fast one because this just looks kind of complicated to me. So couldn't we just ourselves write a new fast path that's really simple and see if maybe that works well? And if that works well, then maybe we'll just use that. So let's take away this code. And just do a new implementation that's really fast but simple. Well, we'll see if it's fast. So first thing I'm going to do is so we'll follow the same model. We'll do the same speed trick to operate on machine words rather than individual bytes. There's no, it's just not worth the trouble to do things on individual bytes. And there's so many different ways to do string comparisons without having to write it yourself. It's nuts. I mean, the C compiler knows how to do an inline comparison, and it actually does a really good job when your length is constant, which ours is not. The libc knows how to do a string comparison, which is highly optimized machine code, but it needs to check for a gazillion special cases. It's going to check if your memory you're comparing is more than 10 megabytes, in which case it will use cache bypassing loads and all this kind of stuff. So way too much complexity. And the bloody CPU has even got an instruction that does string comparisons, but that also is special case for a million different things, and in practice only works well when your strings are large. So it's in some sense it's nuts to me that we're in this position of writing a memory compare function ourselves, because there's already so many of them there. But I think it is actually legitimate because our strings tend to be fairly small, and we don't mind allocating a little bit of extra padding memory on them if that means that we can kind of ignore issues of alignment with word size and that kind of thing. So anyway, I'm going to actually write some code, which I've almost not done at all in this webcasting yet. So there's our empty function, but the first thing we're going to do is go back to our allocation. String new, and previously we already reserved 3 bytes. We already reserved 3 bytes extra. So originally the code had a +1 here. We changed that to a +4, and now we're going to change it to a +8. So what we want is to be able to load an 8-byte 64-bit machine word, because it's 2018. Any interesting machine has 64-bit as the native word size. So then when we write our little loop in here doing the comparison, we're gonna load 64 bits at a time, whereas the LuaJIT one did 32 bits. And another thing we're going to do is we're going to change the interface a little bit. So normally memory compare actually gives you 0 or -1 or 1, or like it tells you, it does a comparison. It tells you if it's bigger or smaller. We don't care. We just want to know if it's the same. So it's not worth the bother to implement the. Well, hang on, let's check for other usages of this. No, it's only used in that one place. So it's not. There's no upside in implementing the mem compare interface, especially since we don't have a slow path based on mem compare. So we will just call this stir equal, and we will say fast string data comparison caveat depends on the way that we're allocating memory in that function. So actually, specifically what we're going to depend on, and we'll write this down. Yeah, so specifically we're gonna assume that strings, the end of a string is always followed by zeros up until the end of a 64-bit boundary. That means that even if we're only interested in the last byte of a string, we're going to load 64 bits. We're going to know that that's going to be a valid memory access, that's mapped. It's not going to segfault, and we're also going to know that anything is any of those padding bytes are going to be zeros, and so we can depend on that for the purposes of comparison. Those assumptions should make this function really simple, and incidentally also efficient, and it should be pretty easy for us to arrange at the time that we allocate things. Again, with the caveat that we've got to make sure that strings are not being allocated and resized and changed in a lot of different places. Something we need to think about, check for afterwards. But for now, this should be a really simple function now, right? We're going to say P. Again, we're going to access them as machine words. Call that Q. And we will say for we're going to count in, make it a little bit more transparent, shall we? We'll say int words equals, that's the number of machine words that we need to compare. And we're going to say that if I don't know if I need those, but anyway, that's beside the point. We're going to say if P So wow, so I'm not the guy who figures out how to squeeze the last cycles out of a C compiler. Whether I need those consts, I'm actually not sure, and whether I should be incrementing the pointers rather than referencing them with a loop index, I'm not sure either. Although thinking in assembly, I don't think it would matter. So that is a function that is hopefully easy to explain. It's called string equal. It's going to return true if the strings are equal. It takes two strings and a length in bytes as arguments. It takes the first string and casts that over to a 64-bit pointer called P, and the second one does the same with a pointer called Q. It calculates how many 64-bit words need to be compared, and then it loops through, and if any of those words is different, it returns false, otherwise it returns true. And it's allowed to access machine words because the string is padded, and it also doesn't need to take the padding into account for the purpose of comparisons because it's padded with zeros. Now let's make sure that hopefully works. If you see some obvious bug, you can let me know. Let's pop down to the string allocation and make sure that we've got those invariants covered. We did allocate some padding, but is it really zero? That I'm not sure. Let's check. The allocation is here. LJ mem new t. So it is writing a zero terminator there. So it kind of looks like we should be also here doing our zeroing out pad bits. But let me just check if that's redundant, because if the allocator is guaranteeing the memory is already zeroed, which I'm not sure about, then we wouldn't need to do that. Trace our way through here to find allocation. Okay, so there's no comment saying that new allocations are guaranteed to be zeroed, so they're probably not. It would be a little unusual. It would be convenient, but it would be unusual. So we won't assume that. But what we will do is, so right now we're writing one null terminator. But what we want to actually write is 8 null terminators. One is the null terminator of the string, and the others are the extra zero padding. And we could actually be fancy and check for the page alignment here, but I don't think it's worth it at the moment. Let's just keep it simple. Let's just say mem set. Make sure we don't mix up the length and fill arguments. Let's say we're going to do a mem set, and the address is going to be string object in memory plus skipping over the string header and skipping over the length. That's where we want to do our fill. We want to fill with 0, and we want to fill 8 of them. Incidentally, a mem set with a constant size here, this is the kind of code that GCC will do a great job of, actually. So this will compile into a very small, probably 1 or 2 instructions to just get the job done. It won't call out to a real mem set routine. This is a case where the fast path in the C compiler actually works really, really well. And then that is now redundant. So what do you think? What's the guess? I give this a 50-50 chance of working the first time. That's probably wildly optimistic. So what we've done, very briefly recapping, and then we'll run the bloody thing. We have taken out first we took out the slow path for interning new strings. And we made it always run the fast path. Then always using the fast path turned out to be way slower than this mix of fast path and slow path, which I still got no idea why. And then we started looking at what was wrong, why that might be, but the fast path routine was a little bit hard to understand. So what we've done now is we've rewritten the fast path routine to be, clever, originally from originally being clever to now not being particularly clever. But we also changed its interface without updating the caller. We also changed its name, so this isn't going to compile. Whereas we used to check if string fast compare was 0. Now we want to check if string Do we call it equal? Yes. If we want to give string equal is non-zero. So, all right, let's just see if it works. I'll indulge in talking more about it if it actually bloody works. Otherwise, we've got a lot of more work to do. Let's run that. So we're going to run the benchmark, which is this life benchmark, and the best time should be about 6.6 billion cycles. The not so great time should be about 8.6 billion cycles, and the really awful, surprising time would be about 14 billion cycles. Let's see what this takes. It doesn't compile. Oops. So what was my... Okay, one step at a time. Variable I was undeclared. I really leave I undeclared. Would I be such a noob? Yes. Okay, one step at a time. Ah, okay. So silly me, I'm passing memset an integer, going out of my way to create an integer for it, when of course it wants a pointer. That's probably a reasonable thing to do. If you're an expert C programmer, you can give me style tips there. I can look at it again when I don't have the webcam making me stupid. Ah, now it compiled. Let's run the benchmark now and see if it did any good or if it did any bad. So we're hoping for, oops, oh okay, it's very fast when it fails. Okay, so I think we totally broke, I think that we totally and completely broke everything. Now the benchmark fails to load, and since we're hacking on the string interning code, it seems entirely likely that we just mangled the string so that the source code didn't kind of load and parse anymore. So let's see what kind of ridiculously silly thing we've done here. There's a chat box on the YouTube, so don't be shy if you see the problem in my code. I'll stop repeating that. You're always welcome to butt in. Oops, and now I see that there have been messages and I haven't answered them. Huh. Sorry, let me read the chat messages. Don't forget to zero out the trailing bytes. Aha, okay. I didn't. Okay, cool. So I've messed something up here, and I guess there are two main things that it can be. It can be that I'm mangling the contents of the string, or it can be that when I'm searching for a matching string, that I'm getting a wrong result. So first of all, is string equal really returning true when the strings are equal, which is what we want? Loops over all of the words. If any of the words don't match, it returns 0, which is false. Otherwise, it gets to here and it returns 1. I certainly don't immediately see a problem with that. So the other main alternative is that, well, let's use the magic of printf, or some kind of assertion perhaps. let us say, yeah, let's do an assertion here. Okay, this is a really easy way, right? So the string equal is supposed to basically be equivalent to memcompare with a slightly different interface. So obviously, if it returns true, then we should be able to assert that memcompare of the string stir data is 0. So that's just asserting that if our, and well, I guess we should be able to do the opposite as well, right? Let's just do a big assertion here that let's put an else here. Yeah, let us do it here. Sorry. What we want to say just a moment. It's really time to break for lunch, but I can't quite put this down right now, so I'm gonna hack on a little bit. Okay, so all I want to do now is a sanity check, and maybe we'll even do that. This is a good place to do it. So we'll just do this in a really simple-minded way. So we will say assert in a very simple-minded way. If so we just do an additional comparison to just say that if our string comparison says they're equal, then memCompare should return 0, and otherwise memCompare should return non-zero. And we'll preempt that compiler error. Just do a make first, make sure that compiles. So now, if we've got an obvious problem in our string comparison, we would or something that actually triggers, we would hope that we're going to get runtime assertion error rather than heap mangling. So if we get an assertion error, then there's something broken in our string comparison function, which will be amusing because it's so simple, and probably someone watching is completely obvious. And anyway, otherwise, it's probably something more subtle. Ooh, now that I think about it, I have some ideas for more subtle things that it could potentially be. Ah, but that's good news. We're going to have to worry about the subtle things anyway, but we got an assertion failure. So we asserted that memCompare should return non-zero when it actually returns 0, which I suppose suggests a false negative. So we said if, so it's this assertion that failed. So we made a string comparison of stir and stir data sx length, and that returned false, which is what got us onto the else branch. And then we did a memCompare of that same data, stir to stir data sx, same length, and memCompare gave us a non-zero result. Okay, interesting. So that would seem to suggest, correct me if I'm wrong, that our string equal function is broken. So how is it broken? We take in two character pointers, A and B, and the length that is in bytes. We convert those character pointers into P and Q, which are machine word pointers. We calculate the number of words, which is the number of bytes divided by 8 rounded up. We loop over that many words. The words are different, we return false. If it doesn't happen for any of the words, then we return true. Okay, so that code, I don't see the problem with it. I'm going to look somewhere else. I think the next most likely, assuming that this is actually correct, then the next most likely thing is that we screwed up the allocation of the padding and that it's not actually filled with zeros. In which case that that we're violating the interface of that function. Okay, so much for making this simple, right? God, it really makes you wonder if there is already some kind of intrinsic or something for doing a mem compare with machine words. I won't go down that rabbit hole just right this second. So here we were allocating our string. We did a mem set. So we allocated the memory here. The total size was the length of the GC string structure, followed immediately by the length of the string, followed by 8 bytes, and we'll just reformulate that: 1 byte of null terminator and 7 bytes of padding. And we could have calculated the minimum padding actually needed, but we didn't do that. Then we initialize the string here. We are manually filling in the string object header fields. Then we are populating the string contents, the mem copy. Then we are filling in the padding, which is located at the address of the string, skipping over header, skipping over the length in bytes, and then the most comical problem in the world is getting the arguments backwards for memset. I already checked it once, but I'll do it again. First is the constant byte, 0, which is what we want, followed by the length, which is also what we want. We'll formulate that in the same way. 1 byte of null terminating and 7 bytes of padding. So that actually looks okay. So I don't see the bug yet, and it's obviously possible I'm missing something obvious. But the next thing I wonder about is like LJ stir resize. So is there anything that actually changes strings? So in other words, supposing, that we're actually successfully setting up our invariant here. You know what we can do? We can do another assertion here, which would test this. So what I want to know now is, am I missing something obvious here? Are we misinitializing this string already now? And we can actually just do that same kind of assertion. We can say assert that so the mem compare this address hang on. I do this elaborate calculation here, but actually that's the same calculation that is done here. So we can shorten that. More. Sorry, I need to just type check that. I shouldn't be digressing, but let's just check. That returns a character pointer. Yes, it does. So it's safe to do arithmetic on that. Okay, and then we can use that again here. We assert that. I mean, we just made a memory copy from the input string into the new string object, and we expect two things. First we expect that a memCompare will say they're the same because we just copied them, so they certainly should be. We also expect that our string equal function will agree. It's going to take the same arguments. So if we didn't initialize the string correctly in the beginning, then it might be reasonable to expect one of those assertions to fail. And it did. That's nice. Okay, so the assertion that our little string equal function would be happy failed. So either we messed up initializing the string, or there's actually just a bug in that tiny little program. So whatever it is, it seems like we've now narrowed the problem down to some of these small number of codes that I just wrote. Sorry, I'm seeing what Yanis is saying in the chat. Not asserting. But the comment was that I'm not asserting equal equals 0 here, but that's actually okay because I changed the interface on string equal. You know, memcopy, it doesn't use a C Boolean true false, 0 false 1 true. Memcopy returns negative for smaller, positive for bigger, and 0 for the same. So in the string equal, I did it a different way, and it returns true if they are equal, so that we shouldn't have to check for 0 there. Okay, so what did we say? We got two options now. One is that we messed up the. I mean, it's always nice to divide and conquer, right? There's two main options now. One is that I got some bug in this function. The other is that there's a bug in the initialization of the padding, so that it didn't come out to be 0. Wow. This is really kind of embarrassing, but I guess that's what live programming is all about, right? We all have these embarrassing times in our private programming lives, and it's just about sharing them with people on the internet. So what I would like to do is check that the padding is really zeroed, and we could just do that explicitly maybe. I'm going to add another assertion. I'm going to assert that if we do a memory comparison, I don't really want to do a memory comparison. I want to compare with the constant. So we're looking for the easiest way to sanity check that the padding was initialized correctly. First, let's just look again at the line of code where we did that. We took the string data at the beginning of the string. We added the length to hop over the actual string data that we want. We said that we want to fill with zeros, and we are filling 1 byte null termination followed by 7 bytes of padding. Obviously correct. Okay, let's just go like this. Let's just go like this. Let's say int I for I is 0. Let's just check those padding bytes. which, okay, that was still the other one failed. Okay, so you're all sworn to absolute secrecy. This never happened. So that little loop, we just after we did the mem set, then we looped over the padding bytes and checked directly that those are zeros, and they are. And then already down here, it's failing the comparison. So we know that the padding bytes are all successfully initialized to 0. So the string equals function is it's still not happy, even though memcopy is happy. So in principle, that means that we've narrowed it down to being a problem. Just 1 second. In principle, that means we've narrowed it down to actually being a problem in the string equal function. Hold on. Excuse me, here we go. Wow, so is there really a bug in this tiny little function? You know, the first thing to do would be to just replace it with something that is even simpler and see if that fixes the problem. Let's do that. It seems incredible to me that there can be a bug in that code and I can't see it, but I guess that there's some kind of selective blindness. So let's write an even simpler comparison function. Is less than. Even more obviously correct than the previous time. So we loop over length bytes, and for each byte we check if the one string is the same as the other string. If they're not the same, we return false. If none of that happens, then we return true. Let's see if that triggers any funny assertions, or what happens if it runs. It runs. Wow. Wow. And the next thing we do, we'll just abort that, we don't care. Let's include the pad bytes in that loop as well, and then see if that has the same effect. I hop that very quickly. That fails. Interesting. Okay, it is something I didn't think of earlier. So we've got two operands here, two strings coming in, and we very carefully set up the invariant that we will always be padded with zeros, but we only have that invariant for one of the strings. We don't have it for the other one. So For now, let's hang on to all of this code, but we'll put back the other one that probably is okay. Okay, so it was yet another thing that I did wrong. I'm just looking in the wrong place. So we're doing the string equality check. We can go down to our assertions. And one of them is this string data from a Lua string that we allocated very carefully with padding, but the other one is from stir, and wow, it's a hailstorm outside. I guess that it will be a challenge for the sound quality while the hail is coming. We'll see how it goes. We just charge on for now because we're making progress. Okay, so that was a bit silly of me. We allocated we allocated this memory S very carefully. So when we get the data here, we should have all the right padded with zeros. But this stir, like what the hell is stir? Where did that come from? That is what we want to know. So that is something that comes in from the outside. It's a string that gets passed in. Okay, so it maybe gets a bit complicated if we want to make this, the strings are padded with zeros invariant propagate out from this LJ string new. It's the kind of thing I don't mind doing in the privacy of a single source file, but this is called from other modules. I don't really want to create the situation where in the entire code base we need to go through and make sure that everything is aligned like that. It's really at the point where I'm going to have a quick check if there is any kind of an intrinsic mem compare. Yeah, no, but it doesn't really work, does it? It would have to be very specific what we need. Let me check anyway. Mem. That's another language. Okay, no, a little language lawyering. Okay, no, never mind that. We got ourselves into this mess. We'll get ourselves out of it. Let's just do something really simple. We'll see if it preserves the performance or not. Let us just make things a bit simpler now. So we'll only do the 64-bit comparisons for the very last. Sorry, we'll exclude the underlined bytes for now. No, before I do that, let me just check. It seems it's such a pity to introduce special cases, but we legitimately do have a problem we need to fix somehow. Let me just check with that really super naive version before we go and replace that with something more clever. Let's just check that it actually was slow. I assume it was. It certainly looks slow. Yeah, okay, that's incredibly slow. So this benchmark would seem to very successfully exercise string interning. Okay, going back to this code, the problem that we have is that actually we can't depend on both strings being padded with zeros. Let's have another look. Maybe we can look with new, more appreciative eyes on the original code. And so what's the magic there? Is this also actually depending on both strings being padded? I don't immediately see any reason that it's not. Okay, I just want to get this working right now, and then we'll come back and see if we can make it a little bit simpler. I'm going to introduce one special case to get us out of trouble now, because we're in deep trouble. That special case is going to be that I can't believe, wrong file. I can't believe that today in 2018 I'm writing by hand a C string comparison function, and I actually don't. This isn't something I should be doing, but I don't know what the obvious alternative is. Anyway, we're going to do the fast. We're going to have a little local fast path inside of this function for the first. So what we're going to do here is we're going to take away that requirement of having things padded with zeros. We're gonna. I'm not completely happy that I understand the original version right now. So maybe I'll come back and think I was being very silly all day. But anyway, what we're going to do now is we're going to only do the whole words that way. Then what we're going to do is another loop. And that's going to be just on the unaligned part at the end. And we're going to say that if okay, so now where's the last underlined address? It's at p length masked. We'll have to test this. Okay, so now we have two loops. The one that loops over the 64-bit words while we have them, and then the second one that deals with the unaligned bit at the end, byte for byte. Let's see if that. Parentheses, which seems like a perfectly reasonable recommendation. I possibly was wrong. It seems to be fine. Do a parallel make. And let's run that. It's broken. Which assertion was it that failed? String equal. Still failing now in much the same way. So reluctantly, this seems like a good time to break for lunch, at which point I'm sure the solution will be much more apparent. Thanks for fighting along with me. This was a surprisingly interesting bug. where we just changed the size of memory allocation in one part of the runtime system, and that caused a slow path to be taken in string interning in a completely different part of the system. There was one specific benchmark that depends on string interning performance and successfully demonstrated that performance difference. Maybe the reason we had this very obscure case exercise actually depends on specifically on the way that benchmark is written. I'm not sure. And so what we're in the middle of doing now is trying to make a simpler and at least as performant implementation of string interning. And it's turned out to be surprisingly challenging, probably because I'm just making silly mistakes, and I blame the webcam. But that's my story, and I'm sticking to it. Thank you for watching, and back after lunch.